Thank you for coming to our talk. We really appreciate that. So if you're in this room, most of you, I think, won't be surprised to see this. You've seen it in the headlines that, I mean, this year has been pretty hot in terms of ransomware, right? So we've seen several new families. We've seen many campaigns, very disruptive. So I hope you agree with me that this has been actually the year of extortion, right? Yeah, so no shocks, right? Also, this might not come as a surprise. I mean, we have seen this, hopefully not on our laptops. But in case you had seen it on your laptop, I hope you hadn't cried too much. But in case you had cried, please cry no more. Because with this talk, we're going to show you an innovative methodology that we have prototyped that will allow for a better world, hopefully with less successful infections. We've tested ShieldFS on WannaCry. Of course, we haven't tested only on WannaCry. And one of the things that we want to point out since the beginning is that there were some files where WannaCry succeeded. So in this specific example, it managed to encrypt something like 200 files, right? It can change, but anyways. So this is okay. I mean, we embrace it. We accept limitations of detection-based approaches. And we go one step beyond. And we put a safe net, another additional layer of protection that will allow to prevent all of these files to be lost forever. And that's why you see zero file loss. No file were lost at the end of the day. We also tested, of course, on other families. As I was saying, we tested it on the major ones, including WannaCry, yes, of course. And in most of the cases, we had successful detection. In some cases, we hadn't, but still, we managed to reach 0% file loss. This is pretty exciting. I mean, I'm really excited to present this because of this. So at this point, I guess that in your mind, there is one question. Why is ShieldFS, why this guy is telling us that ShieldFS is so different? Why is it making something that maybe other system will not able to do? So, we've started something like 1.5 years ago in this research, and there were already other researchers observing how ransomware was interacting with the file system. And one of the things that was remarkable is that ransomware was interacting with the file system in a pretty evident way. So the file system looked like the perfect place to observe ransomware behavior. We went a little bit further than that, and we observed that not only ransomware is remarkable in the way it interacts with the file system, but also it is completely different from how benign application interacts with the file system. So we based this approach on this observation. We based ShieldFS on this observation, and we exploit this idea in two ways. First, for detection. We use this criterion, this observation, to discern benign from ransomware-like processes in an operating system. We also, of course, inspect the memory of the processes to look for crypto primitives, just in case there is some crypto material in there. It's a further confirmation that it's a ransomware-like behavior. And then we exploit it for the second part of our approach. That is for protection. Inside our file system, because ShieldFS, you might have understood from now on that it's actually a file system. From this point on, we also do protection embedded in the file system, in the sense that whenever our file system detects that something is suspicious or remarkably malicious, we do take an additional protection in order to save those files. Of course, now it might look a little bit vague, but please bear with us. So, great. Now let me guide you to the first part of our story, that is, where do we start from to design ShieldFS? So we started from collecting data, and the first question is, where do we look? Where do we observe our traffic, so to speak? Our traffic is actually file system I/O. So you can imagine, you can abstract the file system from the bottom of the user land as a basically a flow of I/O packet requests, I/O request packets, sorry, or IRP. And those are the smallest atomic units of I/O within the Windows file system. And there's actually a pretty nice interface if you want to develop a driver that allows you to hook up very well into that position. It's called the mini filter driver. And that allows you to see basically everything and to register callbacks for every event that you like. For example, here you see the basic data structure that allows you to register callbacks for like before a certain event, before a certain I/O, after a certain I/O. For example, when a file is created or when a file is read, you can use this kind of callbacks in order to register and take action, right? So you can do that before you see an I/O or after the I/O goes down to the actual file system. For example, you can use this interface to log the activity on the file system. What you see on this table from your left to your right is what you can register as an example. You can register the timestamp, you can register the process ID, you can register the process name, anything that you see flowing down to the file system. The last one is the file path. Just one note. One read operation or write operation can result in hundreds or thousands of these I/O packet requests. So if you're writing a giant file, you're going to see many of these requests. So we start with this tool set in our hands, and we install such a logging agent into clean machines. We had 11 volunteers that allowed us to install this agent on their everyday machines. So this was not a lab experiment. It was on real machines that people were using for their real activities every day. And we ended up having something like 2,000 worth of application data. These people were using collectively 2,000 and something more applications. As you can see from the left column, the profiles of the user were various. We had some developers and power users, some office users, some home users, so a good variety, we believe. This resulted in something like 1.7 billion I/O packet requests, so a pretty juicy data set to dig in. Secondly, as I told, we wanted to understand also how ransomware interacted with the file system. So we repeated the same experiment, this time in a controlled environment because we wanted to control the infection. And so we had to use virtual machines. For this, we use Cuckoo just because it's very nice for automation. So we use that. And we installed, I think it was 2 years ago, so 2015. I mean, those were the most prevalent families. So that's what we used for collecting data. An interesting point here is that, well, of course, we are all aware that modern malware can evade virtual machines. So we adopted all the possible countermeasures for that. But on top of that, ransomware poses a specific challenge to this because it needs to have certain content on the machine. So we put real files, realistically looking files. We emulated the same directory tree that we found on the 11 clean machines. So we kind of replicated the environment of a real user. We've installed browser extensions. We browsed through website in order to collect the history. So we tried to make a realistically looking machine so that ransomware had triggers and then the honey files to start. Great. So at this point, we have clean traffic and ransomware traffic. I call it traffic because it's actually traffic. So now the question is, how do we distinguish between ransomware-like or benign? The original title of our work when we conceived it was a self-healing ransomware file system. So before going to the self-healing part, I want to go to the ransomware-aware part. So how do we make our file system ransomware-aware? I'm going to be showing you a few of these plots. So just to give you a guide to read them, on the horizontal axis, you see a quantity. It's going to be a variable from 0 to 1. And on the vertical axis, you're going to see a frequency. So how many times, how popular that value is in our data set. So for example, if you look here, we can divide it into two quadrants. On the top right, you see that many times we see a high value. On the bottom left, few times we see a low value. And the same for the other two quadrants. The variables that we were looking at, for example, were something like folder listing operations. So how many times we have seen in our two data set a process doing folder listing operations. And as you can see, the red distribution is shifted towards higher values. That is an indication, that actually is an evidence that says that ransomware is doing harvesting. This is something that ransomware has to do before starting to encrypt. It has to harvest the system, right? Similarly, ransomware tends to do more reading operations because it has to, of course, read the files and then do something and then write them back. That's why we also see a change, sorry, not a change, but a difference in the amount of write operations in case of ransomware versus benignware. Also, we see that ransomware has a remarkable amount of file renaming operations. Even though this is not required for a ransomware, the ransomware can get through this and obtain the same behavior. We have seen that in the samples that we have analyzed, there is a prevalence of renaming operations. File type coverage has to do with how many different file types a process is interacting with. If you take, for example, Word or, I don't know, Photoshop, they're going to interact with a very limited amount of file types, right? Whereas ransomware, as we know, we have there is a long list of files that it's targeting. So if we look at the diversity of the file types that a ransomware is targeting, we see that it's shifted towards higher value with respect to a typical benign application that only targets a few types of files. File entropy, so write entropy, that is the entropy of the content written, is not that remarkable if you think. I mean, if you look at this, it's not as remarkable as the previous ones. There is no such a huge difference. So this one should not be used alone. Like if you look at the entropy alone, you're going to have a lot of false positives probably, right? Great. So now we have about 6 features that we can look at to tell apart benign and malicious processes. Great. So what do we do with this? Of course, this is the era of machine learning, so why not using machine learning? That's just a joke, but we really use machine learning. So we train a series of classifiers. They are custom classifiers in the sense that we don't use off-the-shelf classifiers. We combine them in a fairly complex way in order to tell, based on the traffic that we have just used, whether there is an indication of ransomware or non-ransomware. So now you have at least a high-level view of what the ransomware-aware part of ShieldFS is. Now let's give you a still high-level overview of what we mean by self-healing. Normally, when you are interacting with a normal system without ShieldFS installed, with no protections installed, what happens is when a ransomware application encrypts or damages or offends, in a generic way, a file, any other processes that tries to interact with that file afterward, it will find, of course, the encrypted file. If you instead look at the system where ShieldFS or equivalent is installed, what we do is anytime we see a write operation on a file from the first time from a process that has not been cleared, we save that file. So every time a process, which we don't know yet if it's malicious or not, it tries to issue a write operation, which can possibly change completely the file, we save that file before letting the write operation through, and this we can do it thanks to the minifilter API. We save that file and then we let the operation through. So in case we have a fresh and freshly made backup of that file. I mean, given like that is not super clear, but now it's time for digging into this. Andrea is the main author of this research, so be very welcome to swap ourselves.
All right. Thank you, Fede, for the wonderful animation.
No worries.
So now we're going to walk into the details of the internals of ShieldFS. And let's start from the detector component. So as Federico briefly mentioned, we use a set of detection models that we obtained by training some custom classifiers. And we train these classifiers starting from the persistent features that Federico showed you. And in particular, we have two types of models. We have a first set of models that we call process-centric ones that have been trained by looking at each process individually. Then instead, we have another kind of model that we call system-centric one that instead has been trained by considering all the data as coming from a single large process that is actually the entire system. So this model, in comparison to the other one, provides a big picture of the entire state of the system. And it is useful, for example, in cases of multi-process malware. On the other hand, the system-centric model can have a higher false positive rate. So we'll see in a bit how we combine this model in a way that actually can make it more effective. And another interesting peculiarity about these detection models is that we don't have just a single model, but we train multiple classifiers. So as shown in this picture, instead of training our classifiers using the entire data that we collected, we split the data in ticks or intervals that are defined by the percentage of accessed files. And for each tick, we train different classifiers. And we organize these models, as shown in this picture, in what we call the multi-tier incremental approach. And this organization, in this approach, has mainly two advantages. First, we have it can speed up the detection process. This is done because we have specialized classifiers that are, as I said, specialized for capturing the behavior of the ransomware during a certain phase. And also, this is really effective in cases of code injection. We know that malware nowadays use such technique to inject malicious code into other processes. So we have that a process that has been benign in the past may turn to be malicious in the future because a ransomware injects malicious code into it. And these models are effective in this scenario because they take into account different horizon in the lifetime of a process. So we have a shorter model, like in this picture, model 1, that takes into account only the recent history of the process, while we have a global model, on the other hand, that instead takes into account the entire history of a process. So the question is how frequently we ask these classifiers for an answer. So during each tick, we query these classifiers simultaneously. And the difference is that during the time when ticks go on, we reset some of these models. So in this case, you can see that at tick 1, model 1 just look at the recent activity in the lifetime of a process. And this, of course, goes on also with the other models. And at a certain point, we may end up in a situation like this one, in which all our model says that a process is malicious. We are pretty sure about it. We can say, OK, this is a ransomware. On the other hand, we can have a situation like this one, where instead, all our detection models agreed in saying that a process is actually benign. But we can also have, instead, a situation in which we are a bit confused. So our classifiers are not pretty sure about the outcome of the detection. So what we can do, in this case, we have a state in which we say that a process is suspicious. And in this case, we leverage the system-centric model that I described before. So in this case, we look at the big picture of the system in order to have more information about the current state of the protected system. And we can also do something more. What we do is we look for traces of crypto functions used by the process. So just a brief recap. We know that most of ransomware families nowadays use block cipher. Block ciphers, they do it because they are fast. And the goal of ransomware is to encrypt all the files of the user as soon as possible, because they don't want the user to notice that their files are slowly being encrypted. And block ciphers work in an iterative way. So they perform different rounds of encryption. And for each round, they need a key to perform the round encryption. So this means that there is a process that is called key schedule that takes in input the user key, so that the key that the user or the developer provided to the cipher. And from that key, it derives a set of sub-keys that are used, each of them in a different round during the encryption. And these sub-keys that are generated during the key schedule are, let's say, respect a mathematical relationship. So the way these sub-keys are generated is known and deterministic. Of course, it depends on the cipher you're using. But there is a mathematical relationship between these values. And these values are stored sequentially in memory for performance issues. So what we can do, this is the situation in which, for example, we can find in memory all these values that are related to the different rounds of encryption. And what we can do is looking in the memory of a process if there is a sequence of bytes that actually match the mathematical relationship of the key schedule. If we find this sequence of bytes, we can say, OK, this is a key schedule, so it means that this process is using a block cipher, is performing encryption. So now you may wonder, yeah, but what about you find randomly some bytes that match this relationship? Well, the probability of finding this scenario is really, really, really low. For AES, that is the most spread block cipher, we have that in the worst case, the probability of a false positive is 2 to the minus 1,344. So we can definitely say that this is impractical, it's unfeasible, and it probably will never happen. OK, so now let's look how all these components are organized into the architecture of ShieldFS. Here we have our processes running in user space. And we have the I/O manager provided by the operating system that allows processes to communicate with the file system and perform action on the file system. So reading a file, writing a file, and so on. And attached to this I/O manager, ShieldFS presents the detection component. So as we already saw, we have different models. We have the process-centric models. We have the system-centric model. And we also have the crypto finder that can look at the memory of a process to spot any artifacts of the use of cryptographic primitives. And then we also have what we call the shielder, that instead is the module that protects the user data. So it is the module that performs the copy before a file is overwritten. And it is able to automatically and transparently to the end user restore the original files when malicious activity has been detected. Here in this picture, we envision to have a secondary drive, so a shadow drive in which we can store our copies. But this is not a fundamental requirement of our system. And if we look specifically at this recovery and protecting process, we can examine the file recovery workflow of our system. So we have that at the beginning, when a process starts, ShieldFS considers it as unknown because it has not enough information to say if it is malicious or not. So in this state, the process is monitored by ShieldFS, and ShieldFS applies a copy on write layer to perform a copy of a file before it is overwritten. And notice that for performance issues, we perform the copy of the file just the first time it is modified. Then we keep this copy in a cache for a certain amount of time, and so if a process overwrites, so modifies a file multiple times in a short time, multiple times in a short time, we perform the copy of the file just the first time. So then, when our detector has collected enough information to say if a process is malicious or not, we can have a case in which we found that the process is malicious, and in this case, we can transparently and automatically restore the original copies. On the other hand, we have that if a process has been detected as has been identified as benign, we can clear the old copies. This is not over, because there is another step that is important. So whenever we say that a process is benign, we then say that it is unknown. So this might sound weird for you, but if you think about it, it's still related to the code injection scenario. So we have that a process that has been detected as benign could turn to be malicious in the future because a ransomware injects malicious code into it. So we have to handle this scenario, and so whenever we say that a process is benign, then we keep considering as unknown, and we keep monitoring its activity. And just a quick thing, if you're wondering how much this costs to the user, the answer is just a couple of cents. In fact, we estimated the storage overhead that our tool imposed to the end users by estimating this overhead by looking at the data that we collected from the clean user that we have been monitoring for a month. And we found out that in the worst case, ShieldFS required less than 15 gigabytes of additional storage. Or if you want to look at the percentage in comparison to the total amount of storage present in the machine, the overhead is less than 9%. All right, so now you probably want to see some more numbers about the test and the evaluation of ShieldFS. And first of all, we evaluated the detection and recovery capability of ShieldFS. So we used almost 1,500 samples. And these samples have never been seen during the training phase. So samples completely new and unseen by our detection models. Here you can see also some families of these samples. And even more interesting, you can see here that most of these families were not present in our training set. So in our training set, there was no sample of these families. This means that our detection models are generic enough also to detect different kind of ransomware activity of different families. And in fact, we achieved a pretty good result, pretty good detection rate. It is 96.9%. But even better, we found that in all our tests, the files that have always been protected by ShieldFS. So there was no file lost during the execution of this ransomware, even in the case of a misdetection. What does it mean? It means that the difference is that in the case a process is correctly detected, ShieldFS can automatically and transparently to the end user restore the original copies. On the other hand, if in the case of a misdetection, this cannot happen, but still we have the copies of the original files in our secure storage, and if when the user notices the infection, can recover the files manually. We also evaluated the false positives of our detector. And to do so, we used a technique called one machine off cross-validation. So basically, we took off the data of one of our 11 machines from our training set. We trained the models, and then we test the models against the machine that we took off from our training set. And we repeated this process for all the 11 machines. You can see here in this table the results of our evaluation. And if you look at the outcome table, you can see that in 9 cases, we did not have any false positives. And in the other 2 cases, we have really, really low false positives, so 0.27, and 0.15%. And also, you can see in this table that is interesting that while the system-centric model alone has generally higher false positives, the combination between the process-centric models and the system-centric one can get us better results. So then we also evaluated the performance impact of our tool. So we performed some micro benchmark, and we identified 3 scenarios that we evaluated for measuring this overhead. And the first scenario is when a file is open and then read. Then we have when a file is open and written for the first time. So in this case, ShieldFS performs a copy of the file before letting the write operation through. And then we also have further open-write operations in which the file has been already copied, so we have the copy in cache, and we don't need to perform another copy. And the results are good in the first and the last scenario. But you can see here that there is a quite high overhead in the second scenario. This is, of course, due to the fact that ShieldFS is performing a copy of the file. However, we did not perceive such a big overhead while we were using machines in which we installed ShieldFS. So we tried instead to estimate and compute the real overhead perceived by the users. And to do so, we leveraged the data that we collected from the clean users. So we aggregated the IRP logs that we collected into a sequence of file system calls. And we mapped this sequence to the 3 scenarios that I showed you before. In this way, we were able to estimate the user perceived overhead, that in this case is on average about 26%. It is definitely lower there than in the previous case, and also acceptable by the user. All right, so now we'll have a little live demo. We're going to test ShieldFS against WannaCry. I tried this demo like 20 times, so I don't see any reason why it shouldn't work, but in case I have a backup video, so don't worry. And the interesting part here is that I'm using a machine that we used for our initial experiments in 2016. So I'm going to start this machine from a snapshot that is February 2016, while we know that WannaCry has been released just a couple of months ago. So this shows that our detection models are generic and can detect even unseen new malware. All right, so first of all, I'm going to download the sample. Okay, as you can see, also the certificate check failed because of the timestamp of the machine that is from 2016. All right. So here is our sample. Before infecting the machine, I'm gonna show you some decoy files that we placed in the machine, and I'm gonna open this tool that allows us to see the logs generated by kernel drivers. So we're gonna see the log produced by ShieldFS during its activity. Now I'm gonna infect the machine, but before doing this, I'm gonna shut down the network. So your laptops are fine. I'm not gonna infect you. Okay, these are the typical files produced by WannaCry when it starts. And we can see here that there is a process that is performing a lot of operation on the disk. So it's reading or writing a lot of files, and in this case is our sample. And we can see also that here our decoy files are slowly being encrypted by WannaCry. So ShieldFS in the meantime is monitoring its activity, the activity of the process. And if everything goes well, we should see some log here. Okay. So here, ShieldFS, the global model of ShieldFS detected suspicious activity, and it just asked the crypto finder to look for further proof. In this case, it didn't find any traces of the AES block cipher, but it still monitors the process, and we see that after 2 other ticks, so when the detection model, the global model detected the process other 2 times in the further ticks, the ransomware is finally detected and killed by ShieldFS. So now, for demo purposes, ShieldFS did not restore the files automatically, but I'm going to do it manually. But of course, this is done usually automatically by our tool. So here I'm going to start our reverter. Okay, that found the process with the malicious activity that the detector identified. And here, you can see the files are slowly being restored. You can see that the same files are being slowly restored. Okay, we can wait for the entire revert process. Okay, that's it. Everything is done. No file lost. We have our files back. Cool. Okay, so to conclude the presentation, I'm going to leave the stage to Federico.
Yeah, but you didn't put an animation for that. Thank you, Andrea. So it seems that we actually achieved. This is what we wanted to have when we conceived this. I still remember in the whiteboard in the lab we had sketches that says we want a file system that natively supports ransomware detection and reverting operation. If you're familiar with ZFS and similar file system, you can already see some similarity of this. The fact is that ZFS does not have any of these ransomware aware capabilities. So this is what we got our inspiration, and we're very, very happy that we were able to make it. We had a detection component that implements a generic detection model. As you have seen, WannaCry didn't even existed when we created that machine. There's no signatures whatsoever. We trained ShieldFS on a few samples, 383 if I remember correctly, and that was it. Now we can detect WannaCry. And the protection, well, you have already seen it in action. So I think, I'm super happy of being able to work with Andrea on this, to be his advisor on this. I think this is time for questions. Just a reminder, there is also an academic paper describing this. So if you want to dig into the details, we've also set up a website where we collect some materials and so on. We're not releasing the code because we have a patent pending, number 27019. For questions, we are available here for brief questions like, do you guys go to the same barber? Yes. Or, but we have for like elaborate questions and long questions such as, why do you guys look bald, right? Bald. We have the wrap-up room. So if you are available for longer questions, just feel free. We have a first question here. I'm going to, yeah. Can you speak a little bit louder, please? Yes. I don't understand the last part of the question. Okay. Oh, I see. So what you're asking, if I'm just repeating both for recording and for making sure that I understood, you're asking if there is a process that is harvesting many files in the system, is there a chance that we might confuse it with that? It might trigger some of the features, not all of them altogether. That's why we have several features. In our experiments, we had applications performing like zip operations or file operations with many files involved and high entropy, and we didn't see any of those false positives. But a file a process that really resembles like ransomware activity with encryption, with harvesting and renaming and everything, well, it's a ransomware or it's a funny program. Thank you. Any other questions? Oh, we have many there. Sorry, we don't know which came first, so.
Sorry? Yeah, that would be great.
Much better.
You were able to identify the crypto algorithm that the ransomware used to use to encrypt the files, the AES algorithm. Out of curiosity, were you able to find their key or any interest in deeper analysis?
Yep. So when you look and detect the key schedule, let's say the first row, the key schedule is the actual key, so the real key that is used for the encryption. So once we recover the key, we could use, for example, that key to decrypt the files instead of using our copies. But this process is unreliable. So detecting the traces of a crypto function is not reliable. You cannot guarantee 100% of files protected and recovered by using such approach. So yes, we could recover the key, but this is not totally reliable. So this is why our approach does not completely rely on this.
How do you deal with concurrency if multiple applications are writing the same file, possibly multiple benign applications, but you said in one diagram that the benign application gets a copy of the file, whereas the malicious application gets the original file?
Yeah, so first of all, we perform the copy of the file just the first time. So the first application that writes that file, in that case, we perform the copy. So, and we store the copy in a secure storage, and we keep that in a cache for a certain amount of time. So the other application can still access that file and write the file, modify it, and so on. And then in a short period, while we have that file in cache, we do not perform any other copies. But once the cache expires, we will perform another copy of the file on the next write operation.
Okay, thank you.
So if you want to see it from another perspective, it's like an extension of an existing backup system that very frequently takes snapshots. So if you have like backups backing up like every half hour, with this, you extend the lifetime of the backup to the last, I don't know, a few minutes or to the last hour.
Okay, thank you.
So going along those lines, from an ESX standpoint, taking snapshots also Two separate questions, sorry. Also, how does it integrate or interact with antivirus products like McAfee or Malwarebytes or anything like that? Because you're doing a lot of read writes, you're doing a lot of sniffing, and both of those are doing that too.
So from an implementation point of view, in this mini filter, with these drivers, with these mini filters, there is like a stack of these drivers, and you can select the altitude of the driver, so the position, which one should be on the top and which one should be on the bottom. So according to the different requirements of the different tools of the different programs, we could place our tool in the right position, without interfering, of course, with the other software.
Thank you.
Do you have some thoughts on like kernel-based malware, ransomware, and second, like Petya, like approaches which would like overwrite and then do the encryption from a completely different environment?
Can you repeat the question, please? Because
the very first part wasn't clear.
So do you have some thoughts on kernel-based attacks, right? That because your system is based on kernel. Just wondering if you have any thoughts on that. And second was ransomware that might, like Petya kind of approaches, right? That overwrite the MBR, then do the encryption from a completely different subsystem, right? That emulates BIOS or something like that.
All right. So this is kind of out of our scope, but in the case, for example, of Petya, even though it does not actually encrypt the files, but our approach in performing the copies and protecting the user data will still be effective against this kind of attack. So you can still try to recover manually the encrypted files.
And if I could continue on the,
sure.
on the kernel type of attack, I mean, our attacker model, as you can clearly see, is the attacker is not in the kernel, right? As it, most of the time is, if the attacker is in the kernel, even if you have an antivirus, I mean, might be too late, right? So I think this opens a completely different research line that stands with how do you ensure that you can monitor from the outside, like in an enclave or from DMA stuff and things like that. But this is a bit, a parallel research line than ransomware, but it's a very, interesting question. Thank you.
Thanks.
Thank you.
Still have, I think, a couple of minutes for questions. If you guys have some.
I had one. If a attacker understood your file system, how would you estimate that they would best try to subvert it? Like if they were to use a different encryption algorithm or something, like what do you see the weakness in your approach?
You're asking about if we can design an evasive malware that precisely
that can
targets.
bypass your detection algorithms.
Well, it's really about how you can evade all of the features altogether. So you have to write a very slow ransomware that doesn't rename many files in a short time, that maybe doesn't rename any files at all, that it writes files very slowly, low level of entropy. So it's kind of against the business model of a classical ransomware. But yes, I mean, if you have enough time, you can design a malware that is, silent enough. We have thought about it, but in the paper there is a section where we describe all the variables that are involved. There are more than what we have explained here. There is the possibility for designing an evasive sample, targeting ShieldFS. But we believe it's pretty, distant from what the attackers want to do. It is probably easier for the attacker to evade the encryption detection than evading the features.
Also, another thing that the attacker can do to make it difficult to be detected, that we did not really test because there is no sample that does this, is like, for example, using a lot of processes. So if you, for example, consider in the worst case, a malware that spawns different processes and each process encrypts just one file. You would see that process is not benign because it's accessing and encrypting just one file. But in that case, that's why we included the system-centric model that instead look at the big picture of the system. So unfortunately, we didn't test it so well because we didn't find any malware that does this. But this could be a way to make our ShieldFS detector job really, really difficult. Yeah. Thank you. I guess maybe, do we have time for
We have
the
time
last
for
question?
the last question?
Yes.
One
Hi.
more question.
So, where does your backup of the original files reside? And if it resides in the file system, have you encountered a ransomware that was able to encrypt the backup of the files?
This is an interesting question. So our backup can be stored in the same file system or for example, in a secondary drive. But the important thing is that we make the folder in which we store our copies not accessible by user space application. So no user space application can write in that folder. Only on the kernel side, so only our module that is in the kernel can write into that folder. So we deny any write operation from the user land. Thank you.
Thank you.